In the Bohr theory of the atom, electrons are found only in allowed energy levels. When we looked at the energy levels, n equals 1, n equals to 2, n equals to 3, and it could go further than that, although it wasn't shown in the diagram. Allowed levels are quantized energy levels, also called orbits. So there is a specific quantity of energy for each level. As atoms absorb energy, they will absorb them in specific quantities that must equate to the difference in the energy levels to where the electron is trying to go or is going to end up in versus where it is if it's going to go on a higher level. And also, if it relaxes to come down to lower levels, the amount of energy that's released is also quantized. And we know that because every atom, every different kind of atom has its own emission spectrum. We can find out what is the difference between the energy levels of the atoms by looking at the wavelength of light that's emitted and knowing what is the energy of that wavelength. So all of this movement of electrons from lower to higher, higher to lower are called electronic transitions or transitions of the electrons between the allowed energy levels. And Bohr called the different energy levels orbits, just like the planetary model where we have orbits of the planets. The lowest level was called the ground state, the lowest possible energy level. And this was the original model of the Bohr atom. But today, with further research, we have changed certain aspects of this model because Bohr's model of the atom failed to explain line spectra of atoms with more than one electron. Hydrogen is the atom with just one electron. And when Bohr applied the emission spectra of hydrogen to his model, it fit perfectly well. He even gave us an equation by which we can find out the energy levels of the energies of different levels, and we can use that to predict the wavelength of light that would be released. We are not going to look at that equation in our course, by the way, but when we apply the same equations or even try to modify those equations to apply to other atoms, things get very complicated, and Bohr's model hence fails to account for the line spectra we observe with anything more than one electron, starting with helium. So in the new model, the modern atomic theory model, electrons do not move in orbits. And that's when we move away from the planetary model for the atom. Instead, we have atomic orbitals. From orbit, we use the word orbitals. And those are the regions in space with a high probability of finding an electron. So unlike a planet which moves in a circular or an elliptical fashion around its star like our sun, when it comes to electrons, there are atomic orbitals. Those are regions. They are not necessarily circular in nature, and we only have high probability of finding an electron within this region. And electrons move very rapidly within these orbitals, and what that gives us is a high electron density. Electron density is another way of saying that the location within its orbital, within the atomic orbital for an electron, where we have a high probability of finding that electron there, we say that it has high electron density. And within the same atomic orbital, if there is a region where there is low probability of finding an electron there, then we say that it has low electron density. The new model is known as the quantum mechanical model of the atom. What does this sophisticated sounding word mean, quantum? Well, we learned even in the Bohr model of the atom that energy is quantized, and this is just a more hi-fi way of saying the same thing by using the word quantum, which is a singular form, just like spectrum is a singular form of spectra. So in the quantum mechanical model of the atom, what we have are specific regions called principal energy levels in which electrons are found. They are not called orbits anymore. We call them atomic. Previously in the slide before this, we call them atomic orbitals. But now we are going to even further refine our understanding of what exactly happens. And we will begin with something called principal energy levels. Um, so wave properties of electrons conflict with specific locations. What that means is that electrons, while they are particles, they are very light, and we already saw that in one of the previous videos that they have very small masses and they have very high speeds, and because of that they have properties which are similar to the properties of light, which is basically that light is a wavelength. And due to those properties of electrons, which are wave properties of electrons, we cannot specifically identify a location where an electron can be found. Because think about it, can a wave be said to be located at one particular point? A wave is, as we saw previously, is the it has that sine curve, the up motion and the down motion as it passes through space. If we think of electrons in those terms, then electrons should not be pinpointed at a specific location as well. So all of this new findings in the nature of electrons led to the quantum mechanical model of the atom, where we specifically developed this model to explain the behavior of electrons. Erwin Schrödinger was an early 20th century scientist who developed equations, and he took into account both the particle nature of electrons and the wave nature of electrons. And according to his equations, we can determine the probability of finding an electron in specific region in space. We'll never be able to pinpoint the location of an electron, but only have knowledge of what would the probability be of finding an electron in that location. But do not worry, we will not be doing any of that, because that is reserved usually for very high level courses at the graduate level. But we will look at the simplified version of this, and that's where we'll spend the rest of our time or rather most of the time in this chapter. What we will learn about is that there are principal energy levels first of all, and those are similar to the original Bohr atom model, where we had the orbits n equal 1, n equals to 2, n equals to 3. We have still preserved those levels. We just call them principal energy levels. Then within each of the principal energy levels there are one or more sub levels, also called subshells, and they are given letter abbreviations S, P, D and F. Those are the 4 sub levels that exist. So each one of these, n equals to 1 may possess one or more of these 4, n equals to 2 may also possess one or more of these 4, and n equals to 3 will possess one or more of these 4, and then further going down, n equals to 4, 5 will also possess one or more of these 4. Furthermore, each of these sub levels is where we find the atomic orbitals. So in the modern atomic theory, when we have atomic orbitals instead of orbits, electrons at the very low level are found within those orbitals, atomic orbitals. Atomic orbitals are found within sublevels, and sublevels are found within the principal energy level. And that's what we are going to investigate in the next video.